Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024. And no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
Attention shoppers! BlendJet's Black Friday sale is on, and it's our biggest sale ever. Stock up for the holidays, because the more BlendJets you buy, the more you save. With over 50 colors and patterns to choose from, there's a BlendJet that's perfect for everyone on your list. Skip the mall madness. We've got you covered with fast, free shipping. What are you waiting for? Go to blendjet.com and take advantage of our epic Black Friday sale. That's blendjet.com.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you, as always, for listening to our podcast. This is Space Nuts, an astronomy podcast for people who are a bit nutty about astronomy, which is a coincidence nonetheless. I am Andrew Dunkley, your host, and with me, as always, Professor Fred Watson, astronomer at large. Hi, Fred.
I'm the space nut at large as well. That's right.
Or one How are you doing, Andrew? On your shoulders. Yeah, I'm good. I'm very good. What about you?
Yes, still breathing, which is always good.
Always an advantage.
It is, yeah.
Now, we've got a lot to talk about today. We've got a couple of interesting questions we'll get to. We're going to talk about an explosion over the Bering Sea. This happened only in December, a meteor explosion, and it seems to have been a pretty darn big one too. And Stephen Hawking, the great man, is being commemorated with 50p. I would have thought his wisdom was worth more than 50p, but he's going to have his face slapped onto a coin. He should have asked the Queen what that's like before he actually went ahead and agreed to it. But then again, he probably had no say in it whatsoever. We'll also hear from Pedro in Portugal, who's asking questions about intelligent design. And Patrick has asked us a question: is astronomy really that boring? In fact, what he's asking is, the old question of data versus reality, converting the numbers into something that people can actually understand and enjoy. So, lots to get through, and we will start over the Bering Sea, Fred, with that explosion in December. What happened?
It went bang.
Yeah, I'm sure it did. Would have been a mighty loud bang, I imagine.
And that's how we know about it, actually. You're quite right. It's back in December. This is an event that took place on the 18th of December, but it's really only been, it's only hit the headlines within the last few days. So where are we? We're exactly 3 months down the track. And the main reason why that is the case is because nobody saw it.
Well, it's a pretty isolated part of the world, is it?
That's
not?
Right. So this was over the Bering Sea. It's a place called the Kamchatka Peninsula, which is part of Russia, and a very uninhabited part of the world.
Well, let's face it, if they saw it, they wouldn't have told anyone anyway.
Who knows? They might have wanted to keep it to themselves. That's right. It's an event that we now know was comparable, although less intense, than the Chelyabinsk meteor, which you and I have spoken about before. That was an object that entered the Earth's atmosphere above the city of Chelyabinsk in the Ural Mountains, also in Russia, back in 2013. And it caused an explosion which, if I remember rightly, was an equivalent of 450,000 tons of TNT. It was many times the Hiroshima nuclear explosion. And it was caused by an object about 30 meters in diameter hitting the Earth's atmosphere at something like 20 kilometers per second. It blew up in the morning sky above Chelyabinsk and created a flash 30 times brighter than the sun, which everybody rushed to their windows to see what had happened. And 88 seconds later, the blast wave hit the ground, smashed all the windows, and many, many people wound up in hospital. Something like 1,200, I think, in Chelyabinsk.
And I take back what I said about the Russians, because I've never seen more footage of one event in my life.
Exactly.
Entire life.
They are right on the ball there. That's right. It's all dash cam footage.
Yes.
So that was an event, that's the last big, what you might call a super bolide. That's the technical term for this, a super bolide, where something hits the atmosphere and explodes like that. Very big one and clearly very significant. And it's actually very fortunate that nobody lost their life in that, because, walls were blown down and things of that sort. So this event, as I said, it's comparable. It was probably about half the impact of the Chelyabinsk one. The explosion is being categorized at about 173,000 tons of TNT, still 10 times the Hiroshima nuclear weapon. But that means it is really less than half the one that entered over Chelyabinsk.
It's still a mighty big explosion.
Yeah. How do we know it happened if nobody saw it? And the answer is because the world is festooned with what are called infrasound detectors. These are detectors that pick up sound waves which are at a much, much lower frequency than we can hear, but actually permeate through the atmosphere. And in the case of the Chelyabinsk event, the infrasound went twice around the world. Wow. And it sort of reverberated for most of the rest of the day. And it was picked up by 20 infrasound monitors. It was the biggest infrasound signal that had ever been detected. Now, this one is not as big as that one, the Bering Strait explosion, but it was the infrasound that actually revealed its existence. And that was then followed up by sort of a few space enthusiasts, one of whom has picked up an image of it entering the Earth's atmosphere. There is basically the explosion can be seen on an image from a Japanese weather satellite, which sits at in a geostationary orbit over that part of the world. The Japanese weather satellite, of course, recording the surface of the Earth and the cloud cover and all of the rest of it. It was actually a meteorologist who trawled through the data from the Himawari 8 satellite is the one that it came from, and it's run by the Japan Meteorological Agency. Simon Proud, he's a meteorologist and actually works at the University of Oxford. So he did have the academic resources necessary to do that, but he did find an image from this satellite that shows a nearly vertical sort of orange streak. And that ties in with the infrasound measurements, which suggest that this thing came in almost vertically, an angle probably about 7 degrees to the vertical.
Wow, that's pretty steep. So it hit us broadside, basically.
Yeah, that's right. Yes. So, and something like 10 meters across, a mass of about 1,400 tons, and the explosion, as I've said, was picked up by these various infrasound detectors. So really quite an extraordinary thing. It's if you look at the airbursts of these small asteroids, I guess is what you call them, a few meters across, over the last 100 years, there have been 3 of them. One was the Tunguska event in 1908. Then there was the Chelyabinsk one. The Tunguska was far more powerful than any of the other 2.
Yeah, I think there was one casualty in that, wasn't there?
There may have been, yeah. It's very hard to pick up what actually happened. It certainly devastated many areas of forest.
Oh, it flattened them, just like matchsticks.
Flattened trees like matchsticks, exactly. And then the Bering Strait one. What is kind of causing people to raise eyebrows is that these all occurred in Russia.
Why is God targeting Russia?
Because there's an answer to that. Because it's the biggest country in the world in terms of its landmass. The area is by far the biggest. I think it's something like is it 6%, maybe 3% of the world's land surface area. So it's really quite a remarkable place in terms of that landmass. It's here we are. It's 3% of the planet's surface area. That's the total surface area of the planet.
Which doesn't sound like much, but when you consider how much the ocean covers,
yeah, that's right. So
3.3% of the entire planet's surface. It's much more a percentage of the landmass.
That's right. Exactly so. So that's basically the bottom line. There is, on one of the websites reporting this, there is basically a diagram showing all the fireballs since 1988, and they're pretty well dotted uniformly all over the world. But the two that stand out, of course, are the Chelyabinsk event and this new Bering Sea meteor, both in Russian territory. So very interesting stuff. We expect things of this size round about 3 per century. We've had two now within the space of 6 years. So
we're going to have a big rest now.
Yeah, we need a big rest. That's right.
Or maybe our estimations are wrong.
Well, it could be. That's right. They're all based on statistical studies, statistical inferences of the number of these objects around.
So who knows when we'll see another one. And look, there's a possibility there won't be one for eons. It's just one of those things. It's pot luck, really.
It is. I suppose this all begs the question, how are we doing in terms of detecting objects like this? And you and I have spoken before about the fact that the US Congress mandated NASA to, first of all, to find all, I think it's 90% of, and once again, this is a statistical total, 90% of all objects bigger than a kilometre, which NASA achieved several years ago, and are now working on objects which are down to 140 meters. So 140 meters is big enough to devastate a city because it would make it almost certainly through the atmosphere. It's a big object. But they are pretty hard to detect because they're small. In terms of being celestial objects, they're shining only by the reflected light of the sun. They're not that easy to detect. And there are still calls out there for infrared spacecraft that might orbit between the Earth and the Sun, looking back at the Earth and actually trying to pick up objects that may hit the Earth's surface. Whether that will happen or not, I don't know.
Yes, they've got the PDCO looking for PHOs.
That sounds right. The PHOs are potentially hazardous objects. What's the PDCO?
The Planetary Defence Coordination Office.
Oh, of course. Off the tip of your tongue.
Yes, I love it. Anyway, it's good to know they're keeping an eye out. But if a mega rock does sort of come towards us, then not sure we can do much about it.
Well, that's right. It all depends on how long you've got. That's the bottom line. If you've got a long time, you can deflect it, and there are already strategies in place to think about doing that. And in fact, some of the research that's going on now with other asteroids out in the asteroid belt is all about how strongly held together are these things? Are they just piles of rubble? What would happen if you blew them up and things of that sort?
Yes. You get a nice fireworks display, I imagine.
You might do, yeah.
All right. More to learn, and we'll keep our eyes out for more of these big chunks of rock as they hurtle towards us. Hopefully not. This is Space Nuts. Andrew Dunkley here, and Fred Watson, of course. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by Tech Radar. This is the one I use. I've been using it for a couple of years, and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons, and there was just something about their business model that I particularly liked, and a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, we're going to talk about a coin. And what's that got to do with astronomy? Well, it's got to do with a great man named Stephen Hawking, who was lost to us last year. But his work will live on for a long, long time to come, as will the 50p coin they're going to put him on.
In the United Kingdom, yeah. Actually, despite what you said in your intro a few minutes ago, they're not going to put his face on the coin.
Oh.
They're going to. In fact, they've done it already. This coin has now been issued. It's got a black hole on it, which is in many ways,
Well, okay. How did they know what it looked like?
It's an artistic depiction of a black
right.
hole. So, and it also has something on it called the Bekenstein-Hawking equation, which is for the entropy of a black hole. It's the amount of disorder in a black hole. It's nice that I think it must be the first coin ever minted that's got an equation on it. And that's quite dramatic. So how has it come about? Well, as you said, we lost Stephen just over a year ago. He died on the 14th of March, 2018. Which I just realized when I was thinking about this last night, that would have been Einstein's 139th birthday.
Is that right?
Yeah. So isn't that curious?
Relatively
because
speaking,
of course
that is a coincidence.
Yeah, of course. Hawking was one of the great relativists of our time, and by a relativist I mean somebody who was a total expert on relativity theory. And he was not bad at quantum theory either, because it was quantum theory that led him in the early 1970s to postulate the idea that a black hole can evaporate, that it could basically frizzle away. Things leak out of it. Of course, the way we understand black holes is that nothing comes out of them, not even light, because their gravitational pull is so great, hence the name black hole. But if all you've got is the theory of relativity, that is true. Nothing comes out of them. But as soon as you throw quantum mechanics into the equation, then there is a way that they can lose mass. And it comes about this is a fairly glib and not terribly accurate summary of what's going on. But it's the fact that quantum theory says that in empty space, you get these virtual particles popping in and out of existence. I'm not making this up as I go along, Andrew, even though it sounds as though I am. So they pop out in and out of existence. And you can imagine a situation where on what's called the event horizon of a black hole, which is the point of no return, basically, you get something that pops into existence like a pair of these subatomic particles. And one's on one side of the event horizon and the other is on the other. So one of them leaks off into space and the other falls back into the black hole. And what that does is causes the black hole to lose mass.
Okay.
In other words, evaporate. Now, this is not a process that happens quickly. If you had a black hole with the mass of the sun, which is actually a modest-sized black hole, it will leak away because of Hawking radiation in no fewer than 10 to the 64 years. So that's a 1 with 64 zeros after it. Yeah. And remember that the universe at the moment is 13.8 billion years old. 13.8 times 10 to the power 9 years. If you think about 10 to the power 64, you're talking about a very long time indeed. So it's a slow process, but it would happen. I have to say that it's never been confirmed experimentally. There have been simulations that have been done where you can do things like replace light waves by sound waves and simulate what might happen. And I think they bear out the idea of Hawking radiation. But it's what made Stephen Hawking a famous name in the world of science back in the 70s.
Yeah, he actually came up with that theory at a relatively early time in his career, didn't he?
Yeah, he was. That's right. Yes, he was.
And I suppose that sort of correlates with the understanding that the mathematical brain is at its best in your youth.
So they say. Mine wasn't, I have to say.
Neither was mine. No,
it's not got any better. I probably told you my claim to fame in regard to Stephen Hawking before, Andrew, but I'll tell you again.
Oh, yeah, I love this story.
He once ran over me in his wheelchair. No, ran into me anyway. He didn't run over me. He ran into me. This was in Cambridge. It was on a Saturday, a very busy Saturday afternoon in Cambridge, where I used to work at the time. And I was out shopping, and this wheelchair came out of nowhere. Didn't stop. I kind of had to leap out the way as it pushed past me. I didn't fall over, but I wasn't far off. And then as I watched it disappear into the distance, I realised who it was.
And this electronic voice went, "Sod off."
Yeah. Anyway, so
it's rather appropriate though that he should be on a 50p coin, because as you mentioned, things can appear and disappear in reality, which, as you said, sounds like you're making it up as you go along. But money does exactly that.
Yes, that's right. So the British 50 pence comes and goes as a virtual particle.
They've stolen the shape of our 50-cent piece too. I just noticed.
Not necessarily, because it's a 7-sided one in the UK.
What's ours, 10? No.
It's 12, I think.
12,
isn't it?
Yeah.
No, it can't be 12.
Is that a dodecahedron? I don't know.
I don't have one here. I thought I had one in my pocket, but I don't. No. I've obviously spent it.
Our 50-cent pieces used to be round, but they got so confused with the 20-cent piece, which was almost the same size.
That's right.
They changed them to this awkward chunk of metal that everyone hates because they're so big and lumpy and heavy and they're no good for anything. You could stop a car with one, but you try to spend them and nobody wants
putting
them.
It across the contact point.
Yes. Yes, they're quite a bizarre-looking coin, our 50-cent piece, if you want to look one up. But they're always a talking point, and this will be a talking point for years to come too, the Hawking P, 50p.
That's right.
Made from Stephen Hawking's P, I understand. Maybe not. This is Space Nuts. Andrew Dunkley here and Fred Watson.
Roger, you're allowed to clear here also.
Space Nuts.
Now, Fred, we're going to bump off a couple of questions. I'm pleased to see that we're actually into the questions for March 2019, which is a coincidence because it's March 2019. So we're catching up slowly but surely.
Yeah.
Now, this one comes from Portugal, Pedro Madeira. Hello, Pedro. Thanks for your question. He says, hello, Andrew. In the first place, let me congratulate you, not Fred, and astronomer at large, wait for it, Professor Frederick Garnett Watson. And I did promise him that I would say that, for your excellent podcast, Space Nuts, which I listen to every time. You're the only one, Pedro. I would like to present a question which it would be great if you could answer in a future podcast. What is the professor's thoughts regarding intelligent design of the universe? I'm actually not very interested in the pseudoscientific or creationism related to this subject, but am more interested in understanding if the initial variables defined at the start of the Big Bang or prior to it are so precisely set that the end goal of the universe is to generate life. Thank you very much once again for your excellent podcast. Please never stop. Oh, we did stop there for a moment. Sorry. Fred, intelligent design.
Yeah, I think I mean I take Pedro's question in relation to his second point. He says he's not very interested in pseudoscientific or creationism related to this subject, but more the fact that it is very interesting that the natural quantities, the physical quantities that sort of define the universe, and they boil down to about six numbers, as the Astronomer Royal, Professor Sir Martin Rees, pointed out many years ago. He had a book called Just Six Numbers. And it's things like the mass of the electron, the speed of light, things of that sort, all of which, if you kind of put them all together and tweak them slightly, you don't have to tweak very far before either you have a universe in which nothing whatsoever happens, no stars can form because there's not enough gravity, or you have a universe in which space is so twisted on itself by its internal gravity that it rips stars and atoms to pieces before they can even form. All of those things are determined by the physical parameters of the universe. So yes, ruling out creationism and pseudoscience, which scientists always take basically they use something called Occam's razor, which is a philosophical tool designed to give you the most straightforward answer to any philosophical question or any scientific question. You interpret.
What does that go? All things being equal, the simplest answer is probably the right one. Is that how it goes?
That's the bottom line. Yeah.
It's in my book.
Yeah. Oh, good. I'll check it out in your book. William of Ockham, his name was. Did you know that?
No.
I think he lived in the sort of 14th century or something like that. It goes back a long way, but it's called Occam's razor. So we apply that, and Occam's razor, is always looking for the most straightforward answer. So in terms of what we've just been saying, though, the physical parameters of the universe, in some ways, they've got to be tuned for life because we're here to prove it.
Yes. Unless we're a figment of our own imagination, which is also a theory in existence.
It is, yeah, that's right. Well, Occam's razor rules that out for a few minutes at least.
Yes.
But it is one of the arguments for what's called the multiverse, the fact that there might be many, many different universes, many of which have these parameters that are not tuned for life, and so there's nobody in them because the end product is not living organisms. It might be something else equally bizarre, but in our universe, it is a sort of principle. It's called the anthropic principle that these physical parameters actually do lead to living organisms. I don't think that's because somebody pressed a button to create the universe and was twiddling the knobs, which would be the intelligent design view of it. Partly because if you invoke that, somebody twiddling the knobs, then you've got to explain where they came from and things of that sort. And actually, the whole need to explain things, in some senses, is bound up with the notion of time, because without time, you don't have any sort of causality. You don't have something saying, well, because that happened, that next thing happened. Time has got to be present for that to be the case. And the nature of time is one of the things we really do not understand at the moment. So these questions do take you into some very deep philosophical and scientific regions where scientists are working on that. We're working on trying to understand time. We're working on trying to understand just how much you can twiddle the physical parameters before you don't get living organisms. There was a paper published, I think, last year, which suggested, because people did various simulations on these things, that actually there's a bit more latitude on some of these physical parameters than we thought there was, that you can twiddle them a bit further than we thought, and you still get living organisms at the other end of it.
Wow.
So it might not be quite as well tuned for life as maybe Martin Rees gave the impression of in Just Six Numbers. But it's clearly an active field of research, and one that I think will produce answers that might turn out to be useful. Wouldn't it be great if we could manipulate time?
It would be, well, I don't know, because then you'd have, I think, catastrophe with so many people wanting to change so many things.
You might be, yes, that's right. And you'd have people saying, I don't know what's wrong with this time machine. It would work perfectly tomorrow.
Oh, that's terrible.
Well, I only joke about time machines.
It's a very good one, though.
Rubbish.
Yeah. I mean, everything we've just talked about, I've used little pieces of in my science fiction novel. Not that I'm trying to flog the book, but I'm trying to flog the book. But multi-universe, I do a sort of a time theory portion with Dr. Fred Wilson, who suggests that all time is running concurrently. So everybody who lived and died, all lived and died simultaneously and at different times. It's a very interesting theory I put in there.
Why didn't I think of that?
Yeah, it's too bizarre for even my brain. But yeah, all of that sort of gets written in, as well as Occam's razor. So I use a lot of what we talk about in the book. So
that's good. Yeah, well, I'm glad it's useful.
Buy it, read it, email me. And thank you, Pedro, for the question. Hopefully we gave you an adequate answer. Adequate. I think we'll cover it, wouldn't it, Fred?
Look, we always strive for adequacy.
Yes, that's as good as I did at school, and I keep on striving for that height. Now we move on to a question from Patrick Healy. He has written the Sermon on the Mount in terms of an email to us describing everything that led up to this question. But basically, I'll just paraphrase. He went to a lecture, a TED talk, in fact, about Jupiter, and was captivated until the talk sort of changed, and he was looking at information that suddenly, in 0.3 of a second, made him bored. So it prompted him to think about the scenario he was confronted with. He was in awe, and then he wasn't. And he said, after writing all this story to me, that's a long way of asking the professor to elaborate a bit on the process of astronomical research, and specifically the transformation of what looks to me to be piles of numbers into these fascinating stories of distant worlds. Am I right? Is what I am seeing as boring really fun to these astronomers?
Yes, because we're all very strange people. No, it's true. This is true of science as a whole, but perhaps it's especially true in astronomy, where you can never grab hold of things to tinker around with them and do experiments, because you're always at the mercy of what the universe throws at us. And what it throws at us is electromagnetic radiation, which is light, and radio waves, and all these other things which we can analyze. And it throws subatomic particles at us, which we can also analyze. And now it throws gravitational waves at us too, which is another way that we can learn about the universe. So these things come to us these days by virtue of some very high-tech equipment that seeks to make measurements. It's the same sort of thing as is used on orbiting spacecraft as well. Things like the Cassini spacecraft that was in orbit around Saturn was also festooned with highly technical pieces of scientific kit, which are making measurements. And often they're using devices like charge-coupled devices, which are basically image sensors. And what they churn out is lots of electrons, which are, they're kind of gated or penned in a way that when you put the thing together, you get an image. But what you're really getting out of it is a stream of numbers. The engineers actually are the people who really throw the graphs up, because they are looking at things like the signal to noise ratio that would come from one of these detectors. They're looking at things like the charge transfer efficiency and various parameters like that. That's something called the readout noise, which is a limiting parameter on that. And that's the raw material of the engineering that is going to be used to grab the astronomical information. So you've got all that to start with. And then as the data start coming in, you have to be aware of the limitations of the device that you're using to detect them. And that too can, put constraints on the quality of the information. And so it's a question of starting with all that and then turning that into meaningful results, which themselves are sometimes only numbers, but they often have implications in terms of, the kind of scenarios that you're seeing out there. And one of the really interesting ones is that some colleagues connected with the European Southern Observatory, which we in Australia are now directly linked with through our strategic partnership, colleagues there have been for 20 years making images with infrared cameras of the very center of our galaxy. And they get numbers out of this, which come from something called VLTI, that is the interferometric bit of the Very Large Telescope. And those numbers can be reconstituted into images of stars. And if you do it over long enough, these stars are moving, and the motion that you see tells you, because of all these measurements that you've made, it gives you this really cool piece of information that they are in orbit around an object that weighs 4.1 million times the mass of the sun. And in the space that is available for that, there's only one thing that it can be, and it's a black hole, going back to the Stephen Hawking story. So that's the exciting bit, when you realize that what you've discovered through all this number crunching is telling you that something is there which is as bizarre as a supermassive black hole. That's where it suddenly becomes exciting. I mean, we often as astronomers see excitement just in the data as it comes in, but the end product is the really exciting bit.
Yes. All right. There you are, Patrick. Hopefully that dispels your concerns about the boredom of mathematics and astronomy. He goes on, he does say something else, and I do want to read this out. Professor Watson does a magnificent job with a splendid voice telling these stories in a way that I can understand, and that is a tremendous service to humanity. How about that, Fred?
Well, that's just made me, I missed that bit, actually, when I was reading the question.
I deliberately skipped it before.
It's a great honour. Look, I feel very fortunate to be in a position where I can spend time understanding these aspects of what astronomers are telling us and turning it into words that I can kind of vaguely understand, and maybe you and a few other people can too, Andrew. Thank you very much, Patrick. I appreciate that very much.
It was a lovely comment, and well deserved, I feel. And as a consequence, Fred, I will be sending you your usual fee, 50p, for each episode.
Well, where is it then? It hasn't turned up yet.
I'm going to start next year on the anniversary of the release of the 50p coin.
50p coin, that's good. All right.
I've got to get hold of one first.
Yeah, I'd like to get one too.
I'm sure the chance will come. Fred, thank you. It's been a great pleasure as always.
Good to talk to you, Andrew, too, and keep up the good work with Space Nuts.
Indeed, and we'll catch you next week. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thank you again for listening to Space Nuts. See you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.